Our previous discussion that we seen when we was talking about this three equation, we observed that we can reduce this three set of this three equation into a single equation in terms of v perturbation. So we are going to look further that how we are going to do that. So to start with that, the first step is to differentiate the equation 6 with respect to y. If you go above, the equation 6 is basically our x momentum equation. So we are going to differentiate the x momentum with respect to y, and then we will get this particular equation. And the second step is to differentiate the equation number 7, which is the y momentum, with respect to x, and then we are going to get this equation. The step 3 is to subtract the equation 9 from the equation 8, and this will give us this particular equation which we have here. And here the pink color terms, these two pink color terms that we are seeing over here, is I just highlighted it that so that we can take something common out of these two terms. In the same way, the green highlighted term that we are seeing over here, we have the common here, the u bar, that we can take as a common, while in the pink term we have the u bar prime that we can take as a common. So writing this equation further, we can write this equation as this, where these terms are combined and shown as a single term, and this pink term is shown over here and this green term is shown over here, and remaining terms are like this. And considering this particular term, we can see that the terms which are in the bracket is basically a continuity equation, so that will go to 0. And still we see in this particular equation there are the u perturbation that we don't want, so we want to eliminate this u perturbation which is in this equation somehow, so that we get a equation only in terms of v perturbation. So for that we will do the step 4 over here, which is to eliminate the u perturbation. What we will do is we will differentiate the equation 10 with respect to x. So when we will differentiate these terms, we will get something like this. And I highlighted over here the this blue term that we are seeing in this, which is nothing but the u perturbation. That is what we want to eliminate from this equation. So what we will do is, from the continuity equation we can write in this way, and then we will take the derivative with respect to y in both sides, then we will get the second equation over here. And when we will substitute this definition that we are getting over here in this the equation which is over here in top, where we have the blue terms. When we will replace those terms, the blue terms, which these two particular definition that we are seeing over here, then we will get this equation over here, and we can further reduce it, and after reducing it we will end up with this particular equation, which is a v disturbance equation. As you can see in this equation, there is only v perturbation, and there are the u, but those are not perturbation, but those are the mean u. So we have only the v perturbation. Now we have only v disturbance equation, and we need to solve only this particular equation. Once we have the v disturbance, from all these relation which we seen in the top, by using that we can obtain the other disturbances. And here we are saying this is a biharmonic operator, and that can be expressed in this form. So now we've seen that we have one equation which is a v disturbance equation. Now we want to solve this equation by considering the wave form. So basically we will consider the perturbation in a wave form, which is a v perturbation that we have over here, which is a function of space and time. and we can express that perturbation in this form, where V hat is an amplitude of perturbation, and these are the exponential term that is basically signifying the character of a perturbation. And we can also express this perturbation in this form when we will take the alpha, which is a streamwise wave number. We will get C here. So V hat is the amplitude of perturbation, alpha is a streamwise wave number, omega is frequency, and C is phase speed. So this is a typical form of a waveform of a perturbation for 2D. When we consider the 3D, where the perturbation is function of x, y, z, and t, where we express this perturbation, so we have the amplitude, and in the wave part of this equation we see that we have the alpha x and beta z. So beta z is the basically telling that this perturbation can change in the span-wise direction. So this is a 3D version of the same perturbation, where the beta is a span-wise wave number. So for the current case which we are dealing, we will consider the 2D perturbation. So it is going to be a little bit more simpler, and we will substitute this perturbation definition into this V disturbance equation that we obtained. So yeah, so before doing that, we will get into some different kind of analysis that generally people do when they are performing the stability analysis. So in general, alpha and omega are complex, and its imaginary part becomes zero depending on what kind of analysis is being done. So there are generally two kind of stability analysis people do. One is the temporal stability, and then there is a spatial stability. So in temporal stability, we can see the diagram in the middle, which is basically showing that at the time initial time you have some perturbation everywhere in the space, and that start to grow with the time everywhere. So the first on the top left corner we have a plot which is showing that the perturbation at time t naught, and that grows with the time. So that comes under the temporal evolution. Then you have the spatial evolution, where you have some perturbation localized in the space with the time, and when the time increases, that perturbation basically evolve, and it evolved in the streamwise direction. At the same time, it also grow with the in the amplitude. So this is study comes under the spatial evolution. Now coming to the mathematics, in the temporal evolution or temporal stability, we consider the alpha, which is a streamwise wave number, as a real, and this is input. So we specify the streamwise wave number, and the omega is output, which is a frequency. So this omega is basically complex in nature, and it is output that comes out of an eigenvalue problem. So considering the V perturbation, we consider in this way, where we have the V hat as amplitude, and in the waveform we have the alpha x and omega t, which can be further expressed in this form, where alpha x is over here and this is c multiplied with the t. So in this particular temporal study, we specify the input as alpha, and we get the c, which is a phase speed, as an output, and this is our eigenvalue for the temporal stability. So we get a complex eigenvalue where we have the cr and ci, which is the imaginary part and real part. So the real part is the phase speed, and imaginary part is something which specify the growth rate of this particular disturbance associated with this alpha input. In the spatial stability, we do things slightly different, where we specify the input as omega, which is frequency and it is real, and we compute for alpha, which is a wave number, and it is complex. So we use the same formulation for the perturbation, but here what we do is we input the omega, which is a frequency, and we get the output alpha as an eigenvalue. And here the real part and imaginary part specify different things, where the real part specify the phase speed real part specify the wave number, while the imaginary part specify the growth rate. Now we have all this detail. So basically here we will look into the temporal stability, and how we will look at how we are going to substitute this perturbation definition into this V disturbance equation that we are getting.